Imagine for a moment that everything you know, the stars, galaxies, and even the fabric of space itself, is contained within something far stranger than you ever imagined. Some scientists propose a compelling and mind-bending theory. Our universe could actually be inside a black hole, a vast labyrinth birthed from a catastrophic event in another universe. When you think back to the Big Bang, the moment our universe burst forth from an unimaginably hot and dense state, you might picture an explosion. But some theorists see it instead as a white hole, essentially the reverse of a black hole. While a black hole pulls everything in with a gravity so fierce that not even light escapes, a white hole hypothetically expels matter and energy outward, and nothing can enter from the outside. This bizarre idea winds seamlessly into the larger tapestry of the multiverse. In this perspective, every black hole in our universe could be the seed, the womb of a new, baby universe. As matter collapses under its own gravity to form a black hole, space-time itself pinches and squeezes, perhaps giving rise to an entirely new cosmos on the other side, a cosmos that inflates, expands, and evolves, just as ours has. If our universe began with a singularity, an infinitely compact point from which space erupted, could this have been the mirror image of another universe's black hole collapse? To appreciate sheer scale, consider the largest known black hole, TON 618. Nestled billions of light-years away, this cosmic titan contains the mass of 66 billion suns. Its event horizon is so vast that, if it replaced our Sun, it would swallow not just Mercury or Venus, but virtually the entire solar system. Within such behemoths, the possibility of baby universes becomes all the more tantalizing. On the grandest scale, geometry further complicates things. The universe may possess a curvature that loops everything back onto itself. In such a reality, there is no true edge, and no definitive center. Every point could be as central as any other. This echoes the nature of a black hole, which from the outside appears to have no discernible interior edge. If, no matter how far we travel, we can never reach the edge of our universe, just as we can never find the center of a black hole. Might it be because they are, in a sense, fundamentally the same entity? While this theory is far from proven, it invites us to rethink what we know and what our universe might actually be nestled within. When we talk about black holes, the conversation often drifts to another science fiction staple: time travel. The laws of physics predict that black holes don't just warp space, they twist and bend time itself. This isn't just theoretical. Clocks, be they mechanical, atomic, or biological, tick more slowly the closer they drift toward the event horizon. Such gravitational time dilation means that an astronaut hovering near a black hole for what feels like a single year might return to find decades, centuries, or even millennia have raced by elsewhere. The idea was vividly portrayed in films like Interstellar. Approach a supermassive black hole, and you, alive, conscious, aging, could leap into the future far faster than anyone who remains at a safe cosmic distance. In this way, black holes can become one-way portals to the far future, a natural time machine powered by the very architecture of space-time. But what about travelling back? Here, physics gets even weirder. Some hypotheses introduce the notion of closed, time-like curves, time loops where, at least mathematically, you could circle back and meet yourself. However, to exit such a loop, you'd need to outrun a light beam or escape the black hole's grip, both of which defy our current understanding of physics and practical engineering. No real-world spacecraft, nor any material known to humanity, could withstand the tidal forces or escape the event horizon once crossed. Even if it were possible, you would be bound within the timeline of the black hole itself, a cosmic echo or repetition, not the ability to rewrite Earth's prehistoric past. While these possibilities are the stuff of dreams and paradoxes, Black holes undeniably teach us that time is far, far stranger near their mysterious boundaries, a playground for both science fiction and serious science. To better appreciate these mysteries, it helps to trace the history of our understanding. In 1783, English natural philosopher John Michell first entertained the idea of dark stars, objects so massive that their gravity could prevent light from escaping. In 1796, famed mathematician Pierre-Simon Laplace echoed a similar idea about gravity overwhelming the escape of light. But it wasn't until 1915, when Albert Einstein finalized his theory of general relativity, that the theoretical groundwork was truly laid for modern black holes. Just a year later, Carl Schwarzschild, serving on the Eastern Front of World War I, found the first exact solution predicting such an object: an infinite crushing of space-time at a single point, what we now call the singularity. Decades passed, and the term black hole itself didn't catch on until 1967, when physicist John Wheeler used it in a public lecture. A new era of research followed quickly. In 1974, Stephen Hawking made the surprising discovery that black holes weren't entirely black. Quantum effects meant they could emit radiation and slowly evaporate, a phenomenon now known as Hawking radiation. The ultimate proof arrived in 2019, thanks to the Event Horizon Telescope, an international collaboration involving over 200 scientists. By linking radio telescopes around the world, they created a virtual Earth-sized telescope, allowing them to image the event horizon's shadow surrounding the supermassive black hole at the heart of galaxy M87. What the world saw wasn't the black hole itself. No light escapes from inside, but the shadow it cast against the backdrop of glowing, swirling matter. This glimpse confirmed long-held theories, providing direct evidence that these cosmic monsters truly exist. Why do black holes matter so much to scientists, and ultimately to all of us? They are at the crossroads of the great mysteries of nature. Black holes hold our best clues to understanding gravity at its most intense, the deep structure of space-time, and the mysterious link between quantum theory and the fabric of the cosmos. By observing them, we push the limits of what we know about the universe's birth, its potential fate, and the invisible components, like dark matter and dark energy, that shape everything we see. For physicists, black holes are nature's ultimate laboratories, letting us observe extremes of density, temperature, and energy that can never be recreated on Earth. Speculation runs wild about their potential. Perhaps one day they might power vast engines for humanity, serve as shortcuts via wormholes through space-time, or open new doors to time travel. Whether or not such visions ever come to pass, black holes fuel our most daring dreams, as well as our deepest scientific inquiries. We find ourselves then at the edge of knowledge, facing phenomena that both terrify and inspire. Black holes are the universe's ultimate riddles, majestic, mysterious, and utterly alien. They represent both the danger of the unknown and the endless promise of discovery. The deeper we investigate, the more we're forced to confront not only the strangeness of the cosmos, but our own place within it, and the cosmic tapestry we are woven into. Perhaps the most profound question to ponder is this: what if the answer to the secrets of black holes is also the answer to the deepest riddles of existence itself? The pursuit of knowledge rarely gives us all the answers, but it always leaves us with new wonders and new frontiers. So as we look up at the night sky, let's keep our curiosity sharp, our awe alive, and our quest for discovery ongoing. The universe is waiting for us to ask the next question, and perhaps one day to unlock the final secret at its heart.